Well, anyways, the moduli space M0n. So this is the moduli space of n marked points on the projective line P1. And yesterday we talked about how this is an algebraic variety, how you can really construct a single geometric object whose points will represent different point configurations on P1. And in this moduli space, we consider configurations of n points up to the action of the projective general linear group of 2 by 2 matrices. And we can account for this action by just fixing 3 of the points to be 0, 1, and infinity. So in our configurations, we can only consider those in which the first point is 0, the second point is 1, and the last point is infinity. And well, here we understand P1 as the complex plane with a distinguished point at infinity added. Okay, then this is an algebraic variety, and we want to have some nice coordinate system on this variety. And we introduced the dihedral coordinates. So how did this work? We can take differences of 2 points in C. One of the points can be infinity. If either of the points is infinity, then the difference is infinity. So I should correct my answer to yesterday's question by Melissa. We, of course, still consider the differences in which one of those points appears, including the infinity point. And then, so we will denote this by ij, and then we will introduce very general cross ratios. So I, j, k, and l are different indices here, so they're pairwise distinct. And this cross ratio is really just a product of 2 terms like this, divided by a product of 2 terms like this, where we swap k and l in the denominator. But there's a lot of those cross ratios. There's n choose 4 of them. That's a lot. And we decide to get a somewhat less redundant. We decide to go to a somewhat less redundant set of coordinates. Those are called the dihedral coordinates. So we take only very special cross ratios which depend actually only on 2 indices. So we take the cross ratio of I plus 1, j plus 1, and j. And we want I and j to be non-adjacent modulo n. So again, I think that more or less the last thing I managed to say yesterday is that those coordinates are in bijection with diagonals of an n-gon. Something is happening here, and then it's the nth vertex. And well, we say that I and j have to be non-adjacent modulo n. This means that if we take I to be somewhere here and j to be somewhere here, they're non-adjacent, so the line between them is a diagonal. If they were adjacent, the line between them would have been an edge, and we don't want this. So really those are nicely combinatorially indexed by diagonals of an n-gon. And then the algebraic relations between those, so this is still way too many coordinates. They're algebraically dependent. They're polynomial relations which connect them all. And those polynomial relations can be read of the combinatorics of those diagonals. So namely, you need the following polynomials to vanish. So Rij is Uij plus the product of UKLs such that the diagonal KL crosses Ij minus 1. And those guys vanish. So these equations, they cut out our variety M0n. And we will use these coordinates to construct a likelihood function or a scattering potential. And then today we will use this function to solve a physics problem to compute the so-called CHY amplitude. So today, in this first part of this lecture, I will finish things that I was supposed to do yesterday. So we compute the CHY amplitude by doing algebra on M0n. And again, the CHY amplitude is the 3-level scalar phi cube amplitude. And CHY stands for Cachazo, Henn, and Yuan. Okay, so let's do this. Let's compute the amplitude. So to compute the amplitude, we need some kinematic data. And our kinematic data is represented by points in the complex space, which is d-dimensional. I don't fix d to before here. And the signature of the metric on this space is 1d minus 1, so something very common in physics. And then from those are momenta vectors, which describe our particles, and from them we construct the Mandelstam invariant, and this is, I think, something you have seen before many times. So what we do here is we simply take the sum of two different momenta and we square it, and the square is understood in the sense of this metric. And then, because we assume our momenta to be on shell, so they themselves square to 0, the only term from this square that survives is the middle term, 2 times pi times pj, and this is our Mandelstam invariant. And the momentum conservation, then rewritten in Mandelstam variables, is a bunch of equations. So for each I, we have an equation which says if we sum all the Mandelstam invariants that involve the particle I, we have to get 0. Okay. Now we will use the Mandelstam variables. So those are the Mandelstams. To construct yet another set of kinematic variables, and those will be the ones that will give rise to our scattering potential. So let me do this over there already. So we introduce new coordinates now. The coordinates are called xij, and those are linear combinations of Mandelstam invariants, where the indices here are ordered, so A is smaller than B, but also both indices are between I and j minus 1. And so those are planar kinematic functions. And I and j are kind of understood modulo n. So ij is a cyclic interval. So we have an ordering of numbers from 1 to n, but this is a funny ordering. So 1 is, of course, smaller than 2, and smaller than 3, and so on, and smaller than n. But then we kind of go back here. So n is followed by 1. And in this sense, j can actually be a number that's actually smaller than I, but we understand these inequalities in the sense of this cyclic order. Okay, so fun facts. You can recover the Mandelstam invariants from those planar kinematic functions. This is not very surprising because there's exactly as many of them as there are Mandelstam variables, and this is just a linear change of coordinates. So the explicit reconstruction formula is not particularly difficult. It's of course also linear, and it involves only 4 terms. So it looks like this. We take xij plus 1, xi plus 1j, we sum them, and then we subtract xij and xi plus 1j plus 1. And now we will use these functions and the u functions to construct a function on M0n. We define a function on the moduli space M0n. And this function is defined by the identity. So the function is called phi x. And this is the product of uij times xij. So if we come back to yesterday's lecture, the uij's are now the functions that kind of parameterize our variety. And xij, if we look for a statistical interpretation of this, kind of are our data. Well, the functions xij, they represent our data, our observations, which kind of again makes sense in the context of physics because xij's, they encounter kinematic data. Okay, so this function for arbitrary complex values of xij, phi of x is called the scattering potential. Or the Koba-Nielsen potential. On M0n. Yes. Well, I know how to write this better. I think this is clear enough. This is the exponent of uij. Okay, and then you can, of course, rewrite this function in Mandelstam variables. And this will look like this. So again, this is straightforward. You know how uij's are connected to sigma i's and sigma j's, and you know how xij's are connected to the Mandelstam variables. So one can check that this holds. So here we take the product over all possible combinations of I and j, so over the pairs of ij such that I and j are non-adjacent. Okay. Well, the problem with this function is that it's a function of complex variables and it's multi-valued, right? We have this regular function and we raise it to a complex power. This is bad because it introduces branches of complex valued analytic functions. And we want to kind of fix this. And we fix this by taking the logarithm. So we do exactly the same thing as we did yesterday in the context of algebraic statistics. And then we take the log critical points. So the log critical point set of phi of x is well defined. It doesn't depend on which branch of its analytic function you choose. And why is this? Well, because when you take the logarithm, this function becomes, and then you take critical equations, this function becomes rational. So we differentiate the logarithm of this function. Then we differentiate the logarithm in a way that we normally do this. And this ends up just, and the logarithmic derivative of this again is some function, so we can continue, we differentiate this logarithm. And we sum over all pairs of ij such that they give a diagonal of an n-gon. And we end up getting a rational function. And these equations, they define the critical, so this equation defines the critical point set. And well, this is an equation which involves the differential d of uij. And from this, we will get a system of equations that connect the functions ij. And well, like a system of equations defined by the parameters xij. And the unknowns will be the functions uij. So we'll want to solve for uij. Yes, so again, we sum over all possible pairs of ij that give rise to the coordinate uij, and those are the diagonals of the n-gon. So I and j are non-adjacent modulo n. Okay. And now we are ready for the scattering equations, actually. Intact. Good, so now we are ready for the scattering equations. So another definition. The CHY scattering equations are the following n equations. So we define the polynomial Qi, not the polynomial, but rather a rational function on M0n to be this function. And the equations are then, well, this function vanishes. And there is n equations. So for each I, we take the sum over the following rational function. So we sum over j not equal to I, we take the Mandelstam invariant, and we divide it by the corresponding difference of points on the moduli space. So here, you should think of those numbers as being given to you. So they're kind of fixed. They define your scattering process, they are what you are given. And you want to solve those equations for the sigma I. So you want to find a configuration of points. So you want to solve for sigma I. And again, one of those points can be infinity. If this point is infinity, this whole difference is defined to be infinity. And if you divide by infinity, you get 0. So just ignore this term if you have an infinity here. So how are those equations connected to what I wrote over there? In a fairly straightforward way, actually. So Qi, if you think about this for a moment, is up to a sign, so either plus or minus, the derivative of the logarithm of the scattering potential with respect to the variable sigma I. So again, phi of x is a function of sigmas, and the parameters that define this function are the Mandelstam invariants or those planar kinematic functions xij. And we want to find critical points of this function. So this is again very similar to maximum likelihood estimation, right? That function is actually a likelihood function, the likelihood function for the model defined by M0n, because these equations and those equations are critical equations for this function. So in particular, we know that the number of solutions to those equations is the maximum likelihood degree of M0n, which I defined yesterday. So because this holds, I will write this down. I said this already, but I will repeat it. These functions these equations are actually critical point equations. A critical point equations for the logarithm of the scattering potential. Good. Now we want to solve those equations. And the first thing you want to do when you're solving equations is to understand how many solutions they have. Because in practice, of course, those are kind of algebraic equations, and algebraic equations are best solved numerically. But to efficiently use numerical algorithms, you need to understand how many solutions to look for, so when to stop. And here's the theorem. The number of solutions to the scattering equations so this is not the theorem. We know that this is by definition the ML degree, M0n. And the theorem is that it's n minus 3 factorial. So it's a big number. There's a lot of solutions. We know that M0n is n minus 3 dimensional. This follows in particular from this representation where we fix 3 points and we have n minus 3 degrees of freedom. And the ML degree turns out to be n minus 3 factorial. So I think in the original paper by CHY, they derived this in kind of some intuitive sense, but also formally mathematically, one can use some arithmetic geometry argument to show that this, so we know that this is a topological Euler characteristic of M0n up to sign, and then this is n minus 3 factorial. So this is kind of a fact that's classically known. Okay. And once we know the number of solutions, we can do something with those solutions, because I promised you that in the end we are going to get the amplitude. And we will really get the amplitude already in a few moments. So first of all, we will define a matrix to work with. So we'll define an n by n matrix. We'll call it capital Phi AB, and we will just take this to be a matrix of partial derivatives. So we take each of the polynomials that define, so each of the polynomials that appear in those scattering equations, and we take the derivative of this polynomial with respect to each variable sigma that we have. So with respect to each coordinate of M0n. Yes? In this, yes, here, this is the generic, exactly generic number of solutions. We don't know for sure what the genericity assumption is, but we know that if you kind of pick them at random, you'll be good to go. So I can't tell what exactly the genericity assumption is, and normally, I don't think there is a way to like tell this clearly, but yes, this is a generic statement. This can be smaller. But for generic data, for something, for non-special cases, you're good. This indeed will be n-3 factorial. Okay, so we define this matrix. This is a matrix of partial derivatives, but then QB is itself a partial derivative. So really we define some Hessian matrix. So this is a Hessian matrix. It's a nice and natural object to define, and this is a Hessian matrix for logarithmic scattering potential. Okay, so now I will tell you some facts without any mathematical proofs. You will just have to believe me because we don't have much time. And I think it's okay if you believe me. So the first fact, the rank of phi is at most n-3. So it's an n by n matrix, but it's always degenerate. And in fact, it's quite degenerate. The rank is at most n-3. It's never n, it's never n-1, and it's never n-2. So that's the first fact. And the second fact I will write right here. The reduced determinant of this matrix. So the determinant of this matrix is of course 0 because it's not full rank. But the reduced determinant, which is denoted by determinant prime of phi, is defined to be the following function. So we take the determinant of phi, ABC, PQR, and we divide it by those differences. AB, BC, CA, PQ, QR, and RP. So a reminder, I think that's still on the board. This is just the difference between sigma B and sigma A. And this guy is phi with rows A, B, C, and columns PQR removed. So there is no fact here yet. I'll just pause for a moment. We know that phi is degenerate, but it has rank n-3. So we hope that if we remove 3 columns and 3 rows, then we will get something non-zero. So the determinant of this is actually a non-zero number, and it all makes sense. So the fact is, this function, the reduced determinant, really only depends on phi. It does not depend on A, B, C, PQR. So it turns out that this matrix, although it's rank deficient, is also highly structured. You don't need either kind of, so all of the n-3 minus are either 0 or all of them are non-zero. And then they're not only they're non-zero, when they're non-zero, they're highly connected, because whatever you do along these lines, for any choice of A, B, C, P, Q, and R, the function that you get will not depend on this choice of A, B, C, P, and Q, and R. And this function will be very important for us in this amplitude calculation process. It's the matrix phi in which we removed 3 rows and 3 columns, and A, B, C, and PQ are just the indices of the removed rows and columns. And now I will write a formula that actually computes the amplitude. And then I will not explain to you why this computes the amplitude, because I'm not a physicist. So this will be a definition for the amplitude. Definition, I mean, in my world, it's the definition. The CHY scalar amplitude is the function given by the following equality. IN equals to the following sum. So we sum the same function over the solutions to the scattering equations. And this is the amplitude. So now let's take a moment to think about this function. It is supposed to be the amplitude, right? So it's supposed to be the function of your kinematic data. And why is this so? Well, because we started from kinematic data, and then this kinematic data was treated as parameters. So we fixed them. And those parameters defined those functions Qi, and we looked for solutions to the system of equations, Qi equals 0. So each choice of parameters defines a different system of equations, and then we solve this system of equations. So the solutions depend on your parameters. So the dependence on the parameters goes here. So these solutions depend on kinematic data. And then you just plug each solution into this function. So a solution is a point in M0n. Those are still those differences. So you can evaluate them. You take the square of this denominator, and you multiply it by the inverse of the reduced determinant of phi. So this is just some mathematical object. There's a function which you can evaluate on this is a function on M0n, and you can evaluate it at the solutions of the scattering equations. Function on M0n. And the solutions to scattering equations are points in M0n. So this is, in a sense, so I think it's physically a very nice story. It seems like people in the scattering amplitude community like the CHY equations a lot. But also independently mathematically, it's a very nice story, right? Because first of all, it has to do something with a very classical variety. So this moduli space M0n, which I defined there, has been around for a while. It's not something that came from physics or from scattering equations. It's a very classical algebraic geometry object. And then it turns out that you can solve some rational functions equations, so some algebraic equations on this variety in order to actually get amplitude. And moreover, it turns out that all of this kind of already existed in mathematics independently within this framework of algebraic statistics. So up to here, we've been doing something in principle completely non-physical. We just took some function and we looked for its critical points. And this function, because of the way it's set up, can be interpreted as the likelihood function of some statistical model, namely of the statistical model given by this variety M0n. And then we used this information that we kind of could have obtained in some statistical context to obtain the amplitude. And that's basically where physics-specific things begin. Because if we were thinking about this in the context of statistics, we would just stop here. We would solve those equations and find our unique point, which gives an actual probability distribution. But in physics, we have to go further. We have to take all the solutions and evaluate a different function on them. So this function is not the same function we started from. We don't sum over the minima of the scattering potential. We sum over the values of those solutions when we we sum over the values of this function evaluated at the solutions to scattering equations. The whole procedure is a tiny bit involved, but at the same time it's quite straightforward and mathematically very clean. And then this is supposed to be easier than Feynman diagrams. So I cannot explain to you why this gives the same result as the Feynman diagrams. You'll have to believe me on that. But that's more or less the story. And I think the moral of the story is that sometimes mathematics that has been around for a while can help you solve physics problems. So in principle, sometimes physics problems turn out to be very mathematical, and if you're lucky enough, somebody did the math for you already. And I would like to conclude this part of the lecture with mentioning some references, because, well, obviously all of this has been around for 10 years, and I have nothing to do with this. So, yes.
The question was whether there was something special about the function that you in the end wrote down, which was this det phi, because just to say, these equations, in fact, in the physics literature first came about very long time back, much before CHY, because it came out in the high energy scattering of high energy string scattering. So there is Grassmannian equations, and there the function that goes in is slightly different. It's exponential of sum of Sij, or sum of what you're calling sum of Xij or Sij, I forget. Anyway, sum of the Mandelstam invariance times a log of sigma I minus sigma j.
I see.
And that is also an amplitude, or at least saddle point approximation to some amplitude. So is there something special about this class of functions that we know? It's just the solutions to these scattering equations that are mathematically nice and well defined. Because there are many different functions you could put instead of this det prime phi. Yes. Would give you different amplitudes.
No, that's a very good question. I think, again, mathematically, this is something that's classically studied in statistics, right? So those functions appear naturally in the statistical context, where they kind of serve as likelihood functions. So they tell you which probability distribution describes your observed experiment best. So I do not know if kind of the physics motivation for also solving these equations comes from like the same place. In a sense, you could think about your Mandelstam invariance, about your kinematic data as something that you observe, something like that you observe in an experiment. And then you kind of just want to find a point in M0n which corresponds to this, or a point in this variety which corresponds to this the best. I, of course, don't know what's the physics behind this, but it's like mathematically, at least it's a very natural thing to do, because there's this statistical interpretation.
In the string theory setting, the physics is very clear. It's because you write down the scattering amplitude, and it literally has e to the Sij log of S sigma I minus sigma j. And so you look for saddle points at large Sij, and those are the critical points of that. So in the gauge theory case, in the scalar phi cubed case, it's less clear. Except I thought in some way that these theories, these amplitudes you can get as limits of string amplitudes. But this is probably much better understood than what I'm saying.
Okay, probably yes. But I think then again, it's a question for somebody who's an actual physicist.
Write the CHY formula in the integral form. So you have you are integrating over the worldsheet. And so if you integrate the top form, which is the basically one of the, look at the top rank homology of the moduli space, and you integrate that form, and then that will give you this det prime phi, the specific function that you found. So there's a natural geometric meaning to what gives you the specific by adjoint scalar amplitude, even just from the geometry of moduli space. You could put many other integrands, but there is an intrinsic meaning to the one that produces the phi cube amplitude.
For Yang-Mills? So
Yang-Mills, the form itself doesn't have any cohomological meaning to the extent we understand. There is, of course, a form, but the one that gives this is the sort of
the one where kind of maybe it all started.
Yeah, that I mean, that I don't know, yeah. That Ashok maybe should.
Related, maybe unrelated question is it obvious when you look at that function det prime phi 1 over Park Taylor square, is it obvious that only has simple poles in the Mandelstam variance?
So that's a good question, because of course in principle here you square things, but I think once you expand this should be more or less clear. Because of course you can write this function as in terms of those variables. Sorry, you mean simple poles in the Mandelstam variables? Oh, that's a good question. I don't know. Not to me. But maybe it is.
So it's definitely true that once you do, when you sum over the solutions, you get something with only simple poles.
Yes.
So I guess the reason I'm asking is because that will give you a way to figure out what kinds of integrands you're allowed to have that will lead to something that is a local amplitude.
Yes, so if... But how do you distinguish them? I don't think it's like meaningful to think about individual summons of this function as functions of Sij, because Sij's define a system of equations. So how do you tell this is always the first solution or this is always the second solution if you change the Sij's? So for me, it's kind of, this function is mathematically meaningful. It's mathematically meaningful to say that this is a function of Sij's. Whether it is meaningful to like take one solution and evaluate this, well, not clear, because also the solutions are in principle complex, right? You cannot order them, you cannot say you take the smallest one.
So maybe just to rephrase the question, the final answer that we get, maybe this is a rational function of the Sij's. From this formula, it's very unclear that it's rational, right? Because the Xij's are not, or the sigma ij's are not rational functions of the Sij's. But this is something which is even mathematically a well-defined question, right? That you write down this expression and then you write down some function, and in the end, you're supposed to get a rational function of the Sij's, which is very unclear from here.
I mean, I don't know how unclear this is in the end. This is a system of rational function equations, right? And Sij's appear rationally here. So they're just the numerators of those.
But the sigma ij's are not rational functions of the Sij.
I think they are. I think they are rational functions.
At least if you like do this for a 4-point amplitude, there will be like a nice rational expression. So I think in general.
In general, they're rational functions.
I think so. Yes. Yes. They are not in general. They are not rational. For lower point, at least we see that they are just. We don't know. Okay, I see.
Very complicated solution, and on that you evaluate something, you get a rational function of sigma ij. That seems very surprising, actually.
I mean, those will be algebraic functions, so in the end, it's not entirely surprising.
But I think it's a general statement that if I sum over the solutions to some rational functions over some zero-dimensional variety, say, well, this would be polynomial, but whatever. Then if the summand that I'm summing over is also rational, then the answer will always be rational. It doesn't matter what the equations are. Yeah. I think that there's many ways that you can see that, but just some results from algebraic geometry that you can use to argue that. I would have to think about that. That's not immediately clear to me.
If I just look at the real section of the moduli space, just on the disk, so that I think there are some choice of Mandelstams for which all the solutions are real sigmas, and even there, in general, they are not rational solutions, is it? I see. Yeah, for lower point probably, but
I mean, for lower point, the degree of the equation is very less.
Yeah.
For higher point, it becomes high degree polynomial.
Yeah.
Okay, more questions on this before we switch gears completely? Don't forget about all of this. No, okay. Then I still have 39 minutes. Well, anyways, in my remaining time, my goal is to convince you that the Grassmannian is not scary. That's kind of the main message I will try to convey. Because, you know, this is a program on positive geometry, and in positive geometry, there is no way around the Grassmannian, so we will all have to make our peace with its existence in our lives. Okay, so that was supposed to be the title of my second lecture. This will be the title of the next 35 minutes. Well, yeah, that's the story. For a mathematician, the Grassmannian is kind of a super nice geometric object, and I think everybody who does algebraic geometry, more or less, loves the Grassmannian. Everybody who does algebraic combinatorics also kind of loves at least the totally non-negative part of the Grassmannian. And of course, it plays an important role in this positive geometry business and in physics these days. It gives rise to the Amplituhedron. But when I talk to physicists, sometimes I encounter some Grassmannian anxiety. So there will not be a lot of mathematical facts today. It's more like we'll just try to see how the Grassmannian is a very natural object and how it is the right thing to look at, kind of. I will not give you a lot of physics arguments for this, but I will try to kind of convey the mathematical intuition between the reasoning of physicists who understood, I think, that the Grassmannian is important for physics. So let's do a recap. That's what Melissa told us yesterday in her first lecture. The Grassmannian K, N is an algebraic variety parameterizing k-dimensional subspaces of an n-dimensional vector space. Dimensional vector space. So in principle, this object defines on a ground field, right? We can look at real vector spaces, complex vector spaces, and even vector spaces over finite fields. So for us, again, as yesterday, this field K will be either R or C. So we'll either look at the real Grassmannian, which is a variety whose points represent k-dimensional subspaces of a real space, or we'll take a look at the complex Grassmannian, whose points represent k-dimensional subspaces of an n-dimensional complex space. Okay. So what do these words mean? Well, it's another example of a moduli space, right? This means that this is a geometric set. It's a geometric object consisting of points. It lives in some higher dimensional complex projective space. So capital N is not the small n, it's some big number. And each point represents a k-dimensional vector space. So again, I will briefly repeat what Melissa told us yesterday. How do we get a single point in a high-dimensional projective space from a vector space? Well, the first guess is so we need a point here is represented by coordinates, by a vector of numbers. So we need some vector of numbers coming from a k-dimensional subspace of an n-dimensional space. Well, the first guess is that you would represent your vector space by a k by n matrix. There's k times n many numbers, n many numbers. So in principle, this is supposed to define a point in a k times n dimensional vector space. But the problem is that there's a correspondence between matrices and points in a vector space, but there is no correspondence between subspaces and points in the vector space, because each vector space has many bases. So this is supposed to be basis vectors written along the rows of this matrix. So there's many bases, but we want in the end to get a unique point in the projective space representing our subspace, and the correct way to do this is by taking a look at the maximal minors. So instead of looking at the entries, we look at k by k minors. K by k minors. And those are called the Pluker coordinates. So I will denote them by Pij because this is a very strong habit. In Melissa's talks, they were delta ij. And there's few of those. Are there few of those? Maybe there are not. Well, anyways, they are the correct numbers to look at, because when you change the basis of your vector space, there's a k by k matrix which defines this change of basis. And all the maximal minors will be multiplied by the determinant of this transfer matrix when you perform a coordinate change. And because they all scale uniformly under basis changes, we get a well-defined point in the projective space. So they define point in the projective space of dimension n choose k minus 1. So there's n choose k minus, they're defined up to a common scalar, and n choose k coordinates defined up to a common scalar define a point in p times p to the n choose k minus 1, in the n choose k minus 1 dimensional projective space. Okay, so I told you it's an algebraic variety, which means that there have to be relations between those minors, and which means that any point that satisfies those relations actually represents a vector of minors of some matrix. So I will not prove in general that both things are true. We will concentrate only on the simplest nonlinear case, GR24. So first of all, okay, it's very important to understand that GR1n is just the projective space, right? It's the geometric definition of the projective space. It's the space of lines through the origin. It's a space of one-dimensional linear subspaces of an n-dimensional space. So GR1n is just Pn minus 1. Sorry. And then GR24 is kind of the simplest nonlinear case. Simplest nonlinear case. So let's try a more or less random matrix. I have not prepared it. It's really completely random. So I claim that any full rank matrix has the following relation between its minus P12 times P34 minus P13 times P24 times P14 times P23 equals 0. So let's check that it's true. P12 is 1, P34 is 5, P13 is 1, P24 is minus 3, P14 is 4, and P23 is minus 2. So we have 5 minus 3 plus 3 is minus 8, which seems to be 0. So this relation actually always holds between the minors. And more generally, for higher k and n, those relations will be quadratic. They will become more complicated. There will be a lot of them. But in the end, they're all fairly simple individually. But now let's try to go back. So I claim that any vector satisfying this equation, apart from the vector of all zeros, gives rise to an actual two-dimensional subspace of P4, of R4. So how do we understand this? So first of all, those coordinates are projective coordinates, homogeneous coordinates. They're defined up to a common scalar. So we can, and one of them has to be non-zero. So let's do an example where P12 is non-zero. So we can think that P12 is 1, and this fixes our scaling. And then this equation kind of degenerates, right? Our equation becomes P34 equals P13 times P24 minus P14 times P23. So what's the linear space? If we have some numbers, one of them is 1, then we have 4 independent numbers, and the last one is determined by these 4. So let's take a look at the following matrix. 1, 0, 0, 1, minus P23, minus P24, P13, and P14. Well, the Plücke coordinate P12 is supposed to be 1. This is true, this minus 1. And P13 is P13 as expected. And then you can also see that like the minor that is defined by the columns 2 and 4, for instance, has a determinant equal to P24, and so on. And finally, the last determinant, which comes from those two last columns, is P13 times P24 minus P14 times P23. And this is supposed to be equal to P34. And this equation and these equations are the same. So it works both ways. There are algebraic relations that connect the minus of the matrix, and any vector of numbers that satisfies such relations actually represents some linear space. And this is a priori not obvious, and this is a very nice fact. This actually is a variety, so you don't need to close it up. You get it automatically. So, okay, time is good. The Grassmannian is a very nice variety. It's irreducible, it's unirational, so those words basically mean very nice in the language of algebraic geometry. Yes? Yes. Yes. Oh, no. Okay, you have 6 variables, but those are projective coordinates, right? So they actually live in P5. So that's how you lose 1, and then you get 1 relation, so you get 4. So yeah, this, again, the Grassmannian lives here. Its dimension is, the dimension of the Grassmannian is also a nice number. It's k times n minus k. So in particular, in this case, it's 2 times 2, it's 4, and it lives in P5, because this number is 6, and this number is 5. Okay. So the Grassmannian is mathematically very nice and very well understood. It's named after Grassmann, who is from the 19th century, so it's been around for a while, it's been studied extensively. So mathematicians really know a lot about the Grassmannian. It's one of the best studied algebraic varieties. And the Grassmannian is, as I've said, very important in positive geometry, and I'll give you at least 3 reasons for this. It's very important in positive geometry. Well, first of all, because the Grassmannian itself carries a positive geometry structure. We have successfully been avoiding, given the definition of a positive geometry, and I will continue in the same spirit. So I will not tell you what formally mathematically a positive geometry is, but whatever it is, the positive Grassmannian, which Melissa defined yesterday, the totally non-negative Grassmannian, sitting inside the Grassmannian is a positive geometry. So I'll be a bit hand-wavy now and tell you that a positive geometry, whatever this is a pair. There's like an algebraic variety and a full dimensional subset inside of this variety, which like has boundaries. It's cut out by inequalities, and hence this notation. And it's a pair that comes with a differential form called the canonical form, which knows about the boundary of this guy. So the canonical form knows about the boundary of this guy, and it turns out that the Grassmannian is a positive geometry. It's one of the simplest examples of positive geometries, in fact. The second reason is because, well, it gives rise to the Amplituhedron. And Melissa explained this to us very well in her 2 lectures. Rise to the Amplituhedron. And the Amplituhedron is kind of the motivating object for positive geometry. It's the point of departure, at least for mathematicians. And then, again, it connects to the worldsheet. It connects to M0n. M0n, which is very important in string theory and also is important in the context of CHY equations, is naturally related to the Grassmannian 2, n. It's a quotient space of the Grassmannian modulo the action of the n-dimensional torus. So again, if we come back to the description of M0n that I gave to you yesterday, you can represent points in M0n by 2 by n matrices, right? So each column is a column of homogeneous coordinates of an element in P1, so a point in P1. And those are only defined up to multiplication by a common scalar, so you can independently scale each row. You can independently multiply each row by some non-zero complex number. And then you want to identify matrices which are obtained from each other by independently multiplying rows by some complex number. And this mathematical notation basically means that we say the 2 elements in the Grassmannian are the same if there's a matrix representative for each of them such that they are related by this multiplication by independent scalars in each column. So, okay, 3 reasons. It is itself a positive geometry, and there is not a lot of known classical examples of positive geometries. It defines the Amplituhedron, and also it is connected to the modular space M0n. Okay. No. Yes, exactly. I'll repeat this then more slowly. Okay. So let's consider some completely random matrix. So this is supposed to represent a point in P1. It's a vector of homogeneous coordinates, which means that this and this are actually the same. So we need to mod out this, and we need to do this in each column. And this is the action of this algebraic torus, because we can multiply only by non-zero numbers. So that's why we mod out not by the action of Cn, but by the action of C star to the n. This is again C without 0. So indeed, if you start from the matrix space, there's an action of the general linear group on the left. And if you mod out by this, you get the Grassmannian. If you further mod out by the action of the torus, you get the modular space. Yes, on the Riemann sphere. Yeah. Then you can solve some equations on this variety, but it exists independently of those equations. Okay, good. But importantly enough, like very importantly, the Grassmannian is a natural generalization of the projective space, right? Because the projective space is the simplest Grassmannian. It's the linear Grassmannian. It's Grassmannian 1, n. And this idea that the Grassmannian is a natural generalization of the projective space is kind of clearly visible in the construction of the Amplituhedron. And I will now try to present this in a hopefully understandable way. So the point of departure for this geometric interpretation of scattering amplitudes, in my understanding at least, is this famous paper of Hodges from 2009, which was already mentioned multiple times this week. So what he did there was he took a look at the 6-point NMHV amplitudes in n equals 4 super young mills. And then he realized that amplitude corresponds to the volume of some polytope. Now, a small physicsy digression. The three-amplituhedron NK4 of Z, as defined by Melissa, computes the n to the k MHV amplitude. So in particular, when k is equal to 1, it computes the NMHV amplitude. On the other hand, mathematically, when k is equal to 1, this is a polytope. And this is also a polytope. So in the end, the idea behind the Amplituhedron is kind of the generalization of this observation by Hodges, where we get some geometric object and we compute the amplitudes as the volume of this object. It's not exactly the volume of this object, but it has some volume interpretation. Anyways, what's important here is that really the baby Amplituhedron is this. This corresponds to a 614 of Z. This matrix Z encodes the kinematic data in momentum twistor space. 4 is the dimension of the momentum twistor space plus 1, which is kind of the same as the dimension of the space-time. K is this K in n to the k MHV, so this defines how many of your gluons have negative helicity, and this number n is the number of particles that you scatter. So all of those numbers have a physical interpretation, and this is your kinematic data encoded in the matrix Z. And well, yes, the Amplituhedron, which stems from the Grassmannian, kind of computes these amplitudes. Well, again, this is the tree Amplituhedron, this is the tree amplitude, tree level. And those amplitudes are computed by computing volumes of geometric sets. Now let us try to see why the Grassmannian is a reasonable geometric set to look at, if you know already that some of your amplitudes come from polytopes. Well, there are several ways to look at polytopes. The first here, so how to look at polytopes? How to look at polytopes? This is more or less clear. The simplest way is by doing the so-called age description. The age description is, well, you define the facets. The quad-dimension 1 faces. Of the polytope. Those are linear, those are hyperplanes, and therefore H description. H stands for hyperplane. Then there is the V description. So that's the convex hull of vertices. And those two are very straightforward. You have your polytope, and right there where it is, you kind of either try to identify its facets or you try to identify its vertices, and those obviously define the polytope. But we will concentrate today on the third way of representing a polytope. So a polytope is a linear projection of the simplex. So A is a linear map from Rn to Rd, and then this is the simplex, the image under this linear map. So this is a linear map that's given by some matrix. In Rd is a polytope. And any polytope can be represented like this. This is slightly less obvious, but this is still true. And the idea behind the Amplituhedron is to take this definition of the polytope, well, a purely mathematical idea. I think the physics motivation was already presented by Melissa. And the mathematical idea is to take this definition of a polytope and carry it into the Grassmannian. And why is this so? Well, because the Amplituhedron stems from the non-negative Grassmannian. And the non-negative Grassmannian, geometrically, by definition, is the intersection of the whole Grassmannian with the positive orthant in the n choose k minus 1 dimensional space. Right? So projectively, this is the simplex, the projective simplex. And we intersect it with the Grassmannian. So this is the Grassmannian analog of the simplex. Analog. Simplex. Analog of the simplex. And now we will just project it. And then the Amplituhedron is a projection. Special projection of the positive Grassmannian. So, right, it's defined by a totally positive matrix, by a matrix with whose maximal minus are all positive. And there is no surprise in this, in the fact that this is a special projection, because the polytope that Hodges discovered was a cyclic polytope, and cyclic polytopes are very, very special, as Melissa said. They have this extremal combinatorial property that they have as many faces as possible under a fixed number, where the number of vertices is fixed. And in the same spirit, the Amplituhedron is a very special projection of the positive Grassmannian. So mathematically, it's a very natural story. So if you know what's a natural generalization of the projective space, and you think it's the Grassmannian, then a natural analog of a polytope is this. Well, alternatively, you could turn to the age description and say that a natural analog of the polytope in the Grassmannian is the intersection of a polytope, of an actual projective polytope with the Grassmannian. But this is slightly harder to understand. So this is something that I think is being studied right now. But this is kind of mathematically nicer, because we also know a lot about this object that we start from. It's the simplest Grassmann analog of the polytope, and this is very, 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 very nice. And because it's so nice, we kind of can also make some conclusions about the Amplituhedron, which is again very difficult, but kind of the key ingredient to the success is that we start from an object that is incredibly nice. All right, so I have 10 minutes left, and now I'm supposed to eliminate your Grassmannian anxiety, but maybe I will spend the last 10 minutes generating it back. I will try to explain why some things become more complicated in the Grassmannian than they are in the projective space. This is again no surprise. The projective space is kind of a linear object. It's not scary. And we've seen that the Grassmannian is in general highly nonlinear. There's a lot of polynomial equations that vanish on it. And this leads to more complicated geometry. And then again, I will not explain this in general. I will just concentrate on the simplest nonlinear case, GR24. So polytopes are geometric objects that are kind of simple. There's a lot of structure to them, but the definition is fairly simple. You take linear equations, and this is a solution to a system of linear inequalities. This is a polytope is the set of solutions to a system of linear inequalities. So in principle, there's nothing high level there. And from the point of positive geometry, polytopes are also well understood. So polytopes are positive geometries. And the canonical form is hidden in the facets. But there is a very clear procedure on how to read off the canonical form from the facets of the polytope. So the canonical form is understood for every polytope, and this is algorithmic and nice. Then we have Grassmann analogs of polytopes. So kind of Amplituhedron, the analogs of polytopes, and you can derive some notion of an associated polytope in the projective space. And there is a notion of the canonical form for this polytope. But the problem is that the canonical form of this polytope is not necessarily connected to the canonical form of the Amplituhedron, because the facet structure can be messed up by intersecting with the Grassmannian. So facets behave interestingly. When intersected with the Grassmannian. And now I will just work out the example of GR24 of its non-negative part. So the non-negative Grassmannian GR24 is the intersection of the simplex with the Grassmannian. Well, the 5-dimensional simplex has 6 facets, right? So this guy has 6 facets. So we are in this Plucker space, so my coordinates on P5 will be the coordinates are P12, P13, P23, P14, P24, and P34. And the facets of this set are given, so the facets of the simplex are simply these coordinate hyperplanes. So P12 and so on till P34 equals to 0, and there's 6 of them. And then you intersect this guy with the Grassmannian. Naively, you would expect this guy, oh, sorry, here it should be equals to 4 also. So naively, this guy should also ideally have 6 facets. You would not like to lose facets when you intersect with the Grassmannian, but you actually do lose facets. So the Grassmannian 2, 4 only has 4 facets. And why is that? Well, let's take a look at the Plucker relation again. And let's take a look at this middle term, which appears with a minus. Well, what does it mean to be a facet of the Grassmannian? We want our facets to be cut out by a single equation on the Grassmannian. So let's see if the equation P13 equals 0 cuts out. Does it give a facet? Well, the answer is no. The answer is no, because suppose you set P13 to be 0. Then your Plucker relation degenerates. So again, a facet would contain of points, a facet would consist of points such that P13 is 0 and all other Pij's are strictly positive. But then you still want to be on the Grassmannian, so those points are on the Grassmannian. So this means they have to solve this equation. But it is impossible, right? You have two terms with positive signs, and whatever positive, strictly positive numbers you plug in, you will never get 0. This has no solutions. This conjectural facet is empty. And that's how you lose two facets, P13 and P24. Of course, if you set P12 to 0, then you have no problem. This term dies, and you have one term with a positive sign and one term with a negative sign. There's no problem with finding positive numbers that solve this equation. So the nonlinearity messes up this phase structure. For the positive Grassmannian itself, this is not a big problem. The phase structure is still very nice and combinatorially very well understood. But more generally, for Amplituhedron, this may present problems. So this means that the Grassmannian is more mathematically interesting than the projective space, and studying positive geometries in the Grassmannian is more mathematically interesting. But then also, as we have seen on that board over there, studying positive geometries inside the Grassmannian gives you answers to more general physics questions. So from computing simply the NMHV amplitude, you can do n to the k MHV for all k. This is a powerful tool for physics, primarily because of this Amplituhedron story. And this is a fascinating object for mathematicians because it's been around for a while. It's nicely structured, but still there are some challenges which make life easier because it's not entirely linear. And I think it is a good moment to stop. Maybe I still have 3 minutes, so maybe we'll have extra time for questions, if you have any.
Thanks a lot. Thanks a lot, Dmitrii. We have time for questions.
Yeah, so a simplex would mean triangle and a tetrahedron and so on, right? That's
Triangle,
that's
tetrahedron, and so on, yes. So
okay.
The polytope with the smallest number of
Yes,
bases.
so let's say that D is equal to 2, then just from a triangle you can map onto, let's say, any n-gon?
Well,
because I'm just imagining that a triangle will only have 3 boundaries, so how I'm not able to
the triangle in R, yes, the simplex in R2 only has 3 boundaries. The tetrahedron has 4 boundaries. A 4-dimensional analog of this has 5 boundaries, and so on. So if you want to get a pentagon, you need to take a simplex in R5, so like a 5-dimensional tetrahedron. So in R4, yeah, well, yes. If you want an n-gon in R2, you need to project from the simplex of Rn. And the vertices of the simplex, of which there will be n, will kind of map to the vertices of the polygon in R2, and that's the idea. So there is a lot of dimensional redundancy here. So kind of the number of vertices will tell you more or less which simplex to project. It's not just a triangle, it can be more higher dimensional.
Thanks.
Okay, let's project the tetrahedron to a square. Yeah, for sure. Okay. This is green. This is a bad color to draw on the blackboard. Let's draw a pink tetrahedron and project it onto a square. Okay, so there we go. We have our tetrahedron. So you kind of do not see that last edge. And you have to believe me that the coordinates of those points are 0, 0, 1, 0, 1, 0, and 1, 0, 0, right? And we want to project it onto a square. 0, 0, 1, 0, 0, 1, and 1, 1. And then, oh, of course, there's one more point, 0, 0, 0. So this 3-dimensional guy has 3 vertices. This 2-dimensional guy has 3 vertices. And we can choose a correspondence. Well, I think it's natural to send the origin to the origin. So we will take this point. Okay, but I think this accounts for some more time for questions, right? We'll send this guy here, for instance. And we will send this guy here. And this guy maybe here. So we want to have a linear map defined by a 3x2 matrix, or 2x3 matrix, 2x3 matrix, yes. So we want to have projection which sends the point 0, 0, 0 to 0, 0. Well, this is easy. But then it should also send, for instance, 0, 1, 0 to 0, 1. So what does this mean? This means that basically B and F is 0 and 1, right? If you multiply this matrix of indeterminate coefficients by this vector, the only thing that survives is the second column, right? And we know the image of the second column is 0, 1. The image of the first column will then be 1, 0. So A and E is 1, 0. And the last column is 1, 1. So C and G is 1, 1. So in this sense, we have a linear map. So there is a linear map from R3 to R2 given by a 2x3 matrix whose entries are 1, 0, 0, 1, 1, 1, which sends the tetrahedron drawn here to the square. Oh, okay. Well, and you kind of see it. Yes, it's a three-dimensional object. You turn on some imagination and think that this point is actually here, and then you pretend you live in the flat space. So kind of this point is above us, and we put it back. So geometrically, this is what this map does. So it gives you a square.
I also have a question. So you emphasized that this construction as a projection of Amplituhedron is mathematically very, 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 very nice.
Yes.
Okay. So I'm curious. Can you imagine some? I mean, this is. I was slightly worried that being so nice that maybe it's unique. But we would like to find generalizations, maybe other positive geometries that may have other applications in physics or elsewhere. So I was wondering if you can imagine some generalizations that are maybe not as nice, but perhaps still reasonable.
Yes, of course. I mean, again, if our starting point is the projective space, and then we start doing this positive geometry business in the Grassmannian, there is at least two other things you can do. So first of all, you can kill the word special. So if you kill the word special, you end up with something called Grassmann polytopes. Polytopes, so those are also interesting geometric objects to study, but their behavior is not as nice as of the Amplituhedron. For instance, it is conjectured that all Amplituhedra are positive geometries. Many Grassmann polytopes are positive geometries, but some are not. So those are not necessarily positive geometries, but sometimes they are. Positive geometries can behave weirdly. But sometimes still nice. So you drop this positivity constraint on your kinematic data, and you still have a well-defined geometric object. This is the first thing you can do and get even further than the Amplituhedron. The second thing you could do is, of course, take a look at one of those descriptions. So you can think about convexity in the Grassmannian, which is a tricky subject, but which is something that I think people are doing right now. In particular, someone in your group is doing this right now, I think. And you can also take a look at this description. So you have a bunch of linear inequalities, and you can ask for a set inside the Grassmannian cut out by some arbitrary linear inequalities. So you take a polytope in the big ambient projective space, and you intersect it with the Grassmannian. And you ask if this is a positive geometry. Well, this, I think, is something I'm working on right now in the baby case. So in GR24, it seems like it also gives you a number of positive geometries which kind of do not arise in this Amplituhedron fashion. But it's also tricky, but I think, again, there is nothing that holds us from studying this as a mathematical generalization, and nothing tells me that this has no physical relevance, because, again, it kind of cuts out some linear region, some region inside the kinematic space by some linear inequality. So this is something one can also study. So yes, basically each of those definitions produces an analog in the Grassmannian, and they are not necessarily the same. I think in general they are not the same.
Thanks a lot. Do we have further questions for Dmitrii? Does not seem to be the case. So let's thank both. Yes, you may. Please go ahead, Alok.
Ramanujan projection, if I look at the moduli space M0n and look at a middle dimension projection on the real section, then, I mean, it gives us essentially the one curvy realization of the Associahedron, right? Is that analogous to this, the fact that Amplituhedron is a projection of the Grassmannian?
I mean, in a sense, yes, but the modular space M0n geometrically is not, in this context, it's not very complicated, right? You can realize M0n as a very affine variety. You can just take a big projective space and throw out some hyperplanes from it, and then do a linear projection. So then you kind of have polytopial regions in this arrangement, and you project them linearly, you get polytopes. So the story is similar, of course. This like map between the worldsheet and the Associahedron is similar in spirit, but I think mathematically it's actually simpler, because in the end you end up with a polytope, with an actual polytope.
Thank you.
Anything else? Okay, so in that case, let's thank again both Dmitrii and Melissa for their great lectures. So this concludes the first week of the workshop. Maybe it's a bit early to say this, but I feel like I wish to say thanks to this wonderful local organization. I think everything has just been impeccable, how we're being cared for, the accommodation, the food, the lecture hall, the scheduling. I mean, it's yeah, I have nothing but positive things to say. So I don't know if they can hear me, but yeah, thanks a lot at this point. Super.
So, you know, just since this is the first week and many of you won't be back next week, thank you everyone for joining, and thank you especially to the speakers for this week, and also to, you know, Johannes, who did you know, a lot of the organizational hard work for making this happen. So, you know, we hope those of you who won't be here next week will come back again. We have many programs, and even apart from that, you know, please do come back. So thank you for coming.